Okay, we'll get started. Any major problems with Lab 4? Any of you still working on it? You? Okay, so remember the due date is today, so as long as you get it done by midnight, you'll be on time. I noticed there was a few common issues with the groups that I helped out. The first was a lot of the problems I saw were caused by the connectivity of the second processor in Platform Designer. So if you're having problems, make sure you check that both processors are connected to the same set of peripherals. Yes?
Whenever we were working on ours, the only way we could get it to run after we made changes was by reconfiguring the SOA. We would have to download the both files.
Well, I was gonna suggest that for the barrier. That solves the barrier problem. Was it related to the barrier? Well, it probably was. If it worked after you reconfigured the soft file, then you probably had things connected correctly in the Platform Designer.
It was really tedious because anytime I made changes in the hello world, you'd have to make and then upload both L files and then reconfigure the SOA. So that would take a while.
Okay, well I'll get to that. That's actually my point number. Oh, it should say 2, but I guess it's supposed to be 1 and this is 2. I'll get to that. I'll come back to that in a minute. But you want to make sure that I saw a lot of cases where the processor 2, CPU 2, wasn't connected to the SRAM or to the pixel buffer, and so it couldn't print out any pixels, or to the, if it's not connected to the DRAM, it wouldn't be able to run at all. So check that. If you have a JTAG UART, or if you still have your GPIOs for the hex digits, the hex displays, the 7-segment hex displays, or the LEDs, that's fine. You don't need to connect the second processor to those if you don't plan on using those with the second processor. Okay, so any questions about that? Okay, number 2, which this should say 2, resetting the barrier. The barrier, I didn't get much of a chance to describe how that worked. Do I? Oh, I don't have it. The barrier works by associating a counter for each CPU in the on-chip memory. And every time a CPU reaches the barrier, it adds 1 to the counters associated with the other CPUs. And then it waits for its own counter to have been incremented for each of the other CPUs. So if you have 2 CPUs, the counter just gets incremented to 1. Right, so I get to the barrier, I increment the other guy's counter, and then I wait for my counter to become 1. Make sense? And then after that, I reset. After that happens, I reset my counter to 0 and proceed. The problem is if you run one CPU multiple times before running the other CPU, the counters get desynchronized. So what will happen there is if I run CPU 0, which is first CPU, if I run it 2 times, then it will increment CPU's 1 counter 2 times, and so CPU 1 will reach its barrier and see the barrier is equal to 2, and then get stuck because it's waiting for it to be 1. Right? So the question is, how do you reset the counters? How do you reset everything back to 0? And because the counters are in an on-chip RAM can't be reset. There's no reset signal for RAM. You can reset a flip-flop or a register, but you can't reset a RAM unless you reconfigure the FPGA, which resets everything on the FPGA, including all the on-chip memory. And so that's why it was fixing your problem, I think, because I think what was happening was you were debugging And it's common when you're debugging to have to restart one CPU multiple times without restarting the other. In other words, anytime you don't run both CPUs together every time you run them, if you don't run them both every time you run them, then they will get stuck at the barrier, right? So if you reach a point where you want to test both CPUs, then you can program both ELF files. You can do the NEOS download on both ELF files, which loads the ELF files into the DRAM, which is the off-chip memory. That's not affected by reconfiguring the FPGA. The DRAM is off-chip. It's a separate chip. So you download the ELF files into the DRAM, and then you reprogram the FPGA with configure soft, and that resets the on-chip memory and thus the barriers. So at that point, they should both start running automatically after the FPGA is configured, and everything should be fine. And the way you described it was exactly the procedure you do. You have to make sure that you download the updated ELF file to both CPUs, and then run the NEOS 2 configure soft, right? That's what you said, and that's perfect. The other option, there's another alternative way to do it, which is takes a little bit more effort. But you can run both CPUs in the debugger and have them both stop, like for example, at the beginning of main, and then you can just reset the counters using the debugger. You can just type set counter 0 equals 0, set counter 1 equal 1, right? So in other words, you'd launch the debugger, and then on both you'd say break main. You'd have to break on both. So this is CPU 0, CPU 1. You'd have these in two separate terminal windows. You'd break on main on both, and then you say probably load after that, and then hit continue, and that'll stop them both at main. At which point you can just say, or actually, sorry, I take that back. You want to break on the barrier. And the reason I say that is because in the barrier code I gave you, the counters are declared as a local variable in there. So if you break on the barrier, you load your code, and then you hit continue. They'll run until they get the barrier, at which point you can type set counter 0. Is it counter or counters? I think it's counters. Equals 0, set counters 1 equals 0. And then you can hit continue here and continue over here. So what should happen is the counters is a local variable inside your barrier code. Now you don't have to be in the barrier to set them, but if you want to set the counters outside the variables, outside the barrier, you'll have to set them according to their address, the address of the counters. But if you're in barrier, you can just use the name counters, the array name. You guys with me? Does it make sense? Now, if you set them on CPU 0, because they are a shared on-chip memory, they should get reset on CPU 1 as well. Unless you didn't connect the on-chip memory to CPU 1, which I've seen that happen too. So the connectivity problem could happen here too, and you can verify that over here. After you set these guys, set the counters on CPU 0, you can then print on CPU 1. You should be able to print counters 0 and print counters 1, and it should say 0 for both after you set them to 0 on the other CPU. Make sense? So you should be able to set them over on CPU 0 and then print them on CPU 1, and the value should be the same. And in order for that to happen, you must have the on-chip memory as a slave to both CPUs. The problem, of course, is that this takes more effort than just to reconfigure the FPGA. So it may be easier, depending on how you're debugging it, to just reconfigure the FPGA. This is a way to do it sort of more interactively. Yes?
You should have the program, when it first starts, set the counter to 0.
No, because the TAs asked about that too. You can't do that because you have to start both programs.
But when you hit the reset button, doesn't it just restart both of them?
Oh, that's true. So if you hit reset, they both reset. And then they're both going to try to set them to 0 at the same time. And you're hoping that one doesn't set it to 0
have to go through the entire
after the other one gets to the barrier. Yeah, you could try that. You could do that. It's a little risky because there's no guarantees that it'll work. But if you don't hit the first barrier until after you process the image, then it's pretty safe. But if you have a barrier right at the beginning of your main function, like a lot of you guys do, like a lot of you have that so they both start printing at the same time. Like, so if you want to see the first frame start printing at the same time, you'd put a barrier at the beginning. But you don't necessarily have to do that. And if you have it after the first frame, then it would give it enough time to do that. Assuming, of course, that you're using the reset button. I think that should be good.
What about, you have it so that the barrier, it'll start it once the counter gets to 1 minus number of CPUs. Can you just do it when it's greater than that?
Yeah, that's another approach too. Yeah, there was a couple groups I worked with where we made that change to try to prevent having to reset them. So in other words, if you had run CPU 0 multiple times and it incremented the other CPU's counter more than once, then the other CPU, when it sees that, it's like, oh, well, it's not 1, but it's 5, so that's good enough. Just go. Yeah, you can do that. That also works. Any other questions? Oh, by the way, if you do it the way that you suggested, where you reset it, you probably are going to want to reset them in main, right? Or you could write your own routine. Well, there's a couple options. You could set it up where you can have unsigned. Those counters were unsigned ints, right? Unsigned int star, and then counters. Remember in C, you might not be aware of this, but in C, an array is just a pointer. So you just say unsigned int star. Star means it's a pointer, and then you can initialize it to be the address of the on-chip RAM, which you can hard code in there, or you can use the symbolic name, which is the on-chip underscore memory underscore 0, I think, something like that, right? So then you could say counters 0 equals 0 and counters 1 equals 0, right? Which would reset them. But there's a problem with doing it this way. The problem is that if you set them to 0 like this, they may get set 0 in the cache, but not in the actual on-chip memory, because the data cache sits between. So you've got the CPU, and there you've got the data cache, which is part of the CPU instead of platform designer. It's built in, and then you've got the on-chip memory. So if you set them to 0 like this, they may get set in there, but the on-chip memory may still retain the original values until the cache gets flushed out and updates the lower level of the memory. So in order to guarantee that doesn't happen, instead of setting them like this, you have to set them using the way I did it in the barrier code, which is the IO write 32, or IO, I forget what it is now. Make sure. Yeah, notice I use this IO write 32 direct, and then I take counters I, which is one of the counters, counter number I. Then I reference that with the ampersand, so it becomes an address. And then I put the count in there, and that 0 is just an offset. So that just, I think it's always 0 in here, yeah. So that's just an offset, which we don't need, because we use the array indexing for the offset. You guys with me? So in other words, what I mean by that is instead of putting a 0, I could also put just I times 4 in there, instead of having the I over here as in brackets. So either way, it makes no difference. But anyway, the point is that doing it this way, you bypass the cache. So there's no risk of having the counters be updated in the cache but not in the on-chip memory. If you use this IO32 direct, that gets translated by the compiler into a store IO instruction as opposed to just a regular store instruction, and that bypasses the cache. Any questions? Also, I mean, you could also, actually, it might be more efficient just to say, you could say IO write 32 direct, and instead of having this counter symbol, you could just put on-chip memory 2_0_base in there as well. Yes?
Does the volatile make it where it doesn't update? It just stays the same?
That's what I thought. Yeah, the volatile was supposed to do that. But after I wrote this, I checked it out. I looked at the assembly code that was generated from this function, and it turned out that even though I had said volatile, it didn't make any difference. It still translated that into a regular store word instruction instead of store word IO. See, there's two versions of the store. There's I think it's STW and STWIO. I think those are the two variations of the store word. The difference is that store word goes through the cache and store word IO doesn't. I thought the volatile would translate any writes to a volatile pointer as store word IO. I think it used to do that in the past, but it's not doing it now. So it's a little. Actually, I don't think the volatile is doing anything for us there. But worst case scenario, it's just redundant. But that's a good question. Okay. Right. Okay, going back to lecture 5. Okay, and the third common issue I saw was the linker settings. So I had this slide in the last lecture, but I didn't talk about it when I was lecturing. So I want to, and there was a few things that came up with regards to this. So the problem is when you create your second processor, hold on, let me back up even more. So when you take your ELF file and you load it into your memory, your DRAM, where does it go? Turns out that it goes according to what's the linker, what the linker address tells it to go to. So the linker is part of the compiling process. So, when you compile your code, it goes through several stages. It goes through pre-processing, and then it compiles, and then the last step is linking, which is where you take all of the object files and you combine them together into a final executable form. That's the linking stage. When you create a library, you don't link. Well, I guess that's not true. You link, but you don't. If you do compile with -C, it just compiles an object file. It doesn't create an executable file. And I think it either doesn't link or doesn't go through the full linking process. But anyway, the linker is what combines all your object code together into an executable file, into an ELF file. And inside that ELF file, it defines the addresses where each section of the ELF file is supposed to go. And when I say section, there's different sections. There's a text section, which is your code, your instructions, and then there's some data sections, and there's several of them. There's read-only data, read-write data, and BSS, which is reserved for your global variables. And then there's the stack and the heap. The stack is where your local variables go, and your heap is where your dynamically allocated memory goes. Make sense? So the linker determines where each of those sections is placed when you load the ELF file. We want the ELF file for CPU 1 to go into a different place than the ELF file for CPU 0. We want them to be in two different parts of the memory. So when you created CPU 1, you set the reset vector and the exception handler, and you gave it an 8 megabyte offset. And the idea with that was that you'd have the first 8 megabytes of the RAM reserved for CPU 0, and then the rest of the RAM, which is 120 megabytes, is going to be reserved for CPU 1. Make sense? That way they don't step on each other. Now you might say, wait a second, why is it that we don't have to do this with any other computer? We don't have to worry about this. Your iPhone, you don't have to worry about this. Your Android phone, your desktop PC, your servers. You don't ever have to worry about keeping programs separated in memory. Why do we have to do it now?
The operating system does the handling.
Exactly, and it's not even the operating system. Technically, it's the memory management unit. So operating systems have virtual memory, and the virtual memory basically makes every program see that it starts at address 0.
Logical address?
That's the virtual address, right? So every program thinks it's the only program running with regards to its memory addresses. It has the whole memory space all to itself. But then there's the page table that converts those virtual addresses to physical addresses, and it's actually the page table through the translation that keeps them all separated into different parts of memory, right? The problem is that we're not using a page table, we're not using a virtual memory system, and we're not using the memory management unit because we're programming for bare metal. And you might say, well, who does that? Well, it turns out lots of embedded systems are programmed in bare metal. So if you're writing code, like say for a wearable device like this, you're probably not going to have a memory management unit because this thing is supposed to be really energy efficient, right? And so why waste power on a memory management unit if you're only writing one program that will ever run on it, and the programmer can be responsible for keeping things separate in memory, right? That's kind of the idea. So this is you might not think this is how it's done, and it's not for a general purpose computer, but for embedded system, it's actually quite common, right? So our goal here is to just keep these two ELF files and all their sections in different parts of the RAM, so we don't need to have a page table, right? So the way you do it in this software is a little strange. We do it by setting the reset vector in Platform Designer. And what that's supposed to do is it tells the linker to keep them separate, to add an 8 megabyte offset to CPU 1's linker sections. However, something odd happens sometimes, but it doesn't happen all the time. I don't know what determines this, and I've been trying to figure this out for 10 years, and I still don't know what's going on here. But for some of your projects, it does this thing where it'll take CPU 1, for instance, and it'll put it in a section called SDRAM 0 before reset, meaning that you've got the reset vector that's 8 megabytes into the memory, but the linker decides, oh no, I want to put everything before that, which of course will cause it to overwrite the other CPU's data, right? So in other words, it's sort of countermanding what you're trying to make it do. I thought this was a bug in the old version of the software. I suspected that this is something that Intel fixed in Cortex Prime 18, which is what we're using. We're using the latest version of the software this semester, as opposed to in the past we were using an older version. But apparently it was either not a bug or they didn't fix it. But this semester I've seen at least one group where this thing came up this problem happens. So to fix it, all you got to do, it's pretty simple to fix. But every time you create a new CPU, or I should say new BSP actually, every time you create a new BSP, which you usually do when you add a new CPU, go into your linker settings and just check that. And if you see something in there that says before reset, just change it so it's in the regular SDRAM 0 section, memory region. You guys with me? So what's happening here is, just to give you an idea, your sections are at the top pane. The middle pane are your memory regions. And so the purpose of this linker script is to map each of the ELF sections with a corresponding memory region. The memory region for if you just use SDRAM 0 or SDRAM controller 0 or whatever whatever the name is, it's fine. But if you have that underscore before reset suffix on there, that's when it causes problems. So make sure you check that. Once you set it once, you don't have to worry about it again. Yes?
So originally when I had everything working, the default settings were on that second one. The TA told us that one of them had to be that.
Yeah,
It was
see-
just originally they were both on the SDRAM 0.
Right, in other words, you weren't affected by the bug. Your settings were as they were supposed to be, and you, because of some bad advice from the TA, evidently, you changed them back to what they would have been if you had been affected by the bug. And I should have made that more clear. I just didn't I kind of thought we were done with this when we upgraded the software, but apparently we still have to go through this. So yeah, just double check that. If you have this bug and you don't catch it and fix it, what happens is you'll run one CPU, and it doesn't matter which one you run. Whichever one you run first, it'll run fine, and then you launch the second CPU, and the second CPU will also run fine, except it will crash the first CPU. And you might say, wait a second, hold on. The code, both CPUs are running the same code, right? The same instructions. They're identical hello worlds. So who cares if they overlap each other? Who cares if they overwrite each other? Because it's the same code. Yes, the code is the same. And I think not only that, but the read-only data is the same as well, because it's the picture, the Gamecock picture, right? And the heap, we don't use the heap. If you don't have a malloc in your code that doesn't use the heap, malloc, or in C++, the new operator is what utilizes the heap data. So we don't use the heap, the text should be the same, and the read-only data should be the same. So you would think it wouldn't matter if both CPUs are using the same memory addresses. However, the thing that does matter is the stack, because the stack represents which sequence of functions have been called and what the values of their local variables are. And because both CPUs are not, they're not running in lockstep, one CPU may call a function before the other one does, for instance, you got to have two separate stacks, right? In fact, that's what differentiates a thread, really, when you think about it, is a stack. Like when you talk about multi-threaded code, every thread is supposed to have its own stack. Every thread has its own function stack, call stack. Make sense? So you want to make sure that the stacks are different. And in terms of the other sections, I don't know, you might be able to use the same for both. But definitely the stack has to be, each processor has to have its own region of memory for the stack. Okay? And I think that's what causes the actual crash. Like when you have one processor running and you run the second and it wipes out the first, it's because of the stack overwriting the stack. You're trying to have both processors use the same stack, and that's certainly going to crash one of them. Mostly because the stack has a return address. And so if you wipe out someone's return address and then they go to return, they'll just branch into La La Land, and they'll branch into some undefined address, and that's not part of a program. And because there's no memory management unit, you don't have a seg fault. Like in Linux, if that happens, in Linux, if you branch off into outside your program, the operating system will intercept it and stop it. You'll see segmentation fault. Or in Windows, you'll get a general protection fault. Or if it's in Android, it'll say the app has stopped responding. Force close, force quit, whatever. But we don't have that. We don't have an operating system to do that. So what you'll end up seeing is that one CPU will just appear to die, and then if you go to attach the debugger won't even connect to it. It'll be like, I don't know what's going on. Or it'll connect and you'll see the stack it'll be in some weird address, right? You guys with me? Okay, so that's my long-winded 3 things to check if you're having issues with Lab 4. The final thing I wanted to mention about Lab 4 was I was a little vague, and this was deliberate, but I was a bit vague on which performance measurements we wanted you to make. We're assuming that, and I don't know, this might be a bad assumption, but as far as I know, the code that you get from Lab 3 should match the code for Lab 4, with the only exception being the barrier that you're adding, right? So when you go from Lab 3, you have your fixed point code working, right? And you've got your cache set up. Well, the cache shouldn't make a difference, but the fixed point is working, right? And you've got your interpolation and all that stuff. The code, you shouldn't have had to change your code from Lab 3. So the number of instructions executed when you go to Lab 4 should be about the same. What we're trying to figure out is how much speed up you get from having 2 processors. Now think about that for a minute. How much speed up do you expect to get? Well, in a perfect world, if I go from 1 processor to 2, then I expect the program should run twice as fast, right? The speed up should be 2. And if I have 4 processors, it should be 4 times as fast. And if I put 100 processors, it should be 100 times as fast. That's what you hope. But in reality, it never works out that way. You never get that kind of scalability with parallel computing, ever. In fact, sometimes, and I've had this happen to me, sometimes you add processors and it slows things down. It actually gets slower, which is totally counterintuitive, but I've had that happen. I had that happen once on a supercomputer. It slowed down as I added processors. And why? Because there's overheads to parallelization. And so in this project, what is our overhead? Well, there's a few things it could be, right? One of the things is that we have 2 processors, yes, but we only have 1 DRAM, so there's only 1 memory that holds the code for the processors and the image, the original image of the Gamecocks thing. There's only 1 of those, and there's only 1 frame buffer. So both processors are running in parallel, but they both have to compete for 1 DRAM and 1 SRAM. And if they both try to access those at the same time, one of them is going to have to yield, which essentially is going to serialize that part of the code, right? One of the processors is going to have to stall while the other one gets access, and then they're going to have to basically take turns, right? So that's one of the overheads. Another one is the barrier. So if both processors are not exactly the same speed, then one of them is going to reach the end of the frame, and thus the barrier, before the other one does, and so it's going to have to wait until the other one catches up. That's another overhead for parallelizing this. It's load balancing, right? We want to be able to balance the load, but you guys know that when you rotate the image, parts of the rotated part of the image go off screen. Like, when you rotate it, you get those out of bounds pixels that you don't have to interpolate. And so depending on which rows of the image you process and what rotational angle you're at, you may have to process more pixels on one of the CPUs as compared to the other, right? There may be a load imbalance, because all we do is sort of naively divide up the rows into half, right? But that may not be the best way to balance out the load, the workload. So if one of the processors has a little bit more work than the other, it may lag behind, and so you'll waste some time at the barrier on the faster processor. And so you have to take that into account when you do your performance measurements, right? So what I'm saying is if your methodology is measuring the number of cycles required for the iteration function, that's not good enough, because that's not a complete picture. You're going to want to measure the number of cycles it takes to calculate all the pixels for the whole frame on each processor, and then calculate your speed up based on that. Actually, what I should say is you want to calculate it on both, and you want to record the number of cycles it takes for the slowest one to finish, and that's the frame time. You guys with me? Yes? For one, well, the problem is if you do it for 1 pixel, that doesn't penalize the system for having a load imbalance, right? So if one gets done first and the other one gets done second, right? Calculating just for 1 pixel is only going to consider, calculating 1 pixel is only going to consider the overheads of having to share the, the shared hardware, right? But if you calculate the time for the whole frame, or whichever one the slowest is, then you get a total frame time. And an easy way to do that, it's pretty easy to do that because you got the barrier there. So when you hit the barrier, after you get past the barrier, you can get the cycle count, and then you can just look at whatever the cycle count. So cycle count goes into something called, I call it time new. And so the frame time is going to be time new minus time old, and then you reset your time old to be the time new, right? So if you do this, if you have this code after the barrier, this will calculate the time it spent since the last barrier. So you're measuring barrier to barrier or frame to frame. And this way, you can measure this just on this way you only have to have one CPU doing this. You don't have to do it, you don't have to worry about connecting the CPU 1 to the performance counter. Because you'll notice, if you look at these lists of components that I said you have to share, I don't have the performance counter listed there. And so, you might not have it on this, you might not have the second CPU, may not be able to talk to the performance counter. And so this way, if you measure the time spent since you exited the last barrier, you get a frame time, right? Does it make sense? So this will give you a speed up, an overall speed up, because assuming, of course, you go back and you compare the average frame time. You do this and you get a sense of how long it takes, how many cycles per frame in the 2 processor implementation, and then you would do this for the 1 CPU implementation as well, and then you would take the ratio, and that would be the speed up. Make sense? So it's going to be interesting to find out what kind of speed ups you get. I mean, obviously you can't get more than 2. If you're getting a speed up greater than 2, something is wrong. If you're getting a speed up less than 1, there's probably something wrong there too. If you're getting a speed up close to 2, that's pretty good, and if it's closer to 1, then you're not getting good scalability. Right? Scalability meaning that the more hardware you add, the faster you should get a return for that investment.
So the maximum it could be is 2.
Yeah, you can't do. Although we often get reports that claim more than 2, but it seems impossible. I don't see how it could be more than twice as fast by having 2 processors. Yes?
From what I remember, you were talking about timing. We did that in the second lab, and then we had to comment that out because we were adding the performance counter.
Oh yeah.
So I'm getting confused. So you're saying rerunning time when we're doing cycles in the third one?
Yeah, yes, yeah, it's a little confusing. I meant cycles here. When I say time, cycles are time,
Okay.
but every cycle is 1/50 of a second. In lab 2, we were also measuring time, but we were using the interval timer, and the interval timer was also measuring clock cycles, but it used a different operating principle. It would issue an interrupt every so many ticks, and then it would increment the tick counter, which is a global variable in your code. Whereas now with the performance counter, you don't have the overhead of having an interrupt handler. You just whenever you need to, you go out and you grab the performance count, the cycle count, sorry. Right? So that's what I meant. When I say time could mean ticks or cycles or however you're measuring time. Okay. Okay, so let's now talk about the next lab. So, and the next lab, yes?
This is like unrelated to both labs, but like what on the syllabus, it's like listed we have a final exam.
Yes.
What should we expect on that?
So this will be the first time I've had a final. My plan is to just ask fairly fundamental questions about things you've done in the class. It is designed to ensure, to catch, so it's designed to be your only individual grade. And so the idea is that if only one of the group members are actually writing code and doing the work, and the other group member isn't doing anything, the final exam will allow the group member who's actually been working to, to have some, to measure that, basically. So I'm just going to ask basic questions about, what's a performance counter do, what's it for, what is a memory map, and what is a master and a slave, and maybe basic questions about the frame buffer or interpolation. So I'll give you more details before the final, so you know exactly what to expect. But in a general sense, it's just going to be easy questions that anybody who's been working through the lab should be able to answer easily. Okay. Okay. So in the next lab, we're going to switch to a different application. We're going to the real goal here is to scale up. We want to add more processors. We want to go up to 4 processors. But at this point in the semester, everyone is pretty sick of the rotation code, right? Because we've been doing this for 3 labs now, right? We've done 3 labs of the image rotation. So at this point, we want to mix it up and try a different application. And the one that we switched to here is the fractal generation. So some of you might have heard what a fractal is. It's a graphic that is generated entirely from code, as opposed to the way that we're doing it now, which is where we take an existing graphic, like the logo, the Gamecock logo or whatever picture you're using for your rotation code, and we're loading that into the, so basically it's something that a human being created that we load in, and then we use an image transformation routine to, distort it somehow, rotate it or whatever. Fractals are generated entirely from software, which is pretty neat, I think. I think it's pretty cool. So we don't have to load anymore. We don't have to actually put an image in. It gets generated. Fractals are also cool because they have these repeating patterns that repeat infinitely as you zoom in. So they have like infinite level of detail. So unlike a regular picture, like the graphic that we have now, if you were to zoom in on it, it would eventually just pixelate and become nothing. Whereas a fractal has these details, and if you zoom in on one of these places that has details, that has some kind of features, like around the edges of these, where these little patterns are, if you zoom in, the patterns repeat. You see these repeating patterns, and so you can keep zooming in and zooming in. It's pretty neat. Yes?
Yeah, so the code for this, we're going to have to use recursion on this, right?
No, you don't need recursion.
But just because, like, the image itself.
No, in fact, you don't want to use recursion here because if you tried to use recursion, it would overflow the stack pretty quickly because because you just keep going and going and going, right, with this stuff. So fractals are kind of neat also because you see these really cool looking shapes, some of which look kind of organic looking, even though they're just mathematical. They're generated mathematically, even though they look like, they look organic. It's kind of cool. The one that we're doing in this class is the Mandelbrot Set. It's the most famous one. You might have seen this picture before. I think they have it I think Carter has a picture of that or a little exhibit on the first floor of Swearingen. The Mandelbrot Set looks like this. It has these kind of bulbs on it. First thing you might ask is, wait a second, it's a set? What is a set? A set is a collection of values. So when you're talking about a set, something is either in a set or it's not in a set, right? So how does that translate to this multicolored graphic? That doesn't make any sense. Well, it turns out that what's being shown here is just a regular. This is a plot. So you've got the horizontal axis is x and the vertical axis is y, and the Mandelbrot set is being. This picture is being discretized. So you take the plot, you take the 2D space, and you just associate a pixel with each point in here, right? And so each one of those pixels represents just an x and a y value, right? It's just a grid of x and y values. The pixels that are black, the black pixels, are pixels that are in the Mandelbrot set. So black means you're in the set. Anything other than black is not in the set. So really what this is it's a bunch of black pixels here arranged in these bulbs that represent x, y values that are in the Mandelbrot set. The brightly colored pixels are pixels that are not in the set, but they were almost in the set. And the brightness of their color represents how close they were to being in the set, right? So if you take this and you zoom in to the edges of where the black meets the colored pixels, what you're looking at are essentially the black pixels are the ones that are in, and the fringe ones are the ones that are sort of almost in to varying degrees, where the brightness of the color represents how close those pixels were to being in the set. Does that make sense? Right? So if I just randomly point to any pixel, that pixel will have an x and y value, and then if I'm pointing to a black area, it means it's in it, or anything else, it's not in it, but depending on how bright the pixel is I'm pointing to defines how close it was to being in it. Okay, so now the other thing is what you're really seeing is not a x and y here. It's not a you think of x and y as a vector of size 2, as a tuple, right? What this is really showing is just a set of single values, but they're complex values, they're complex numbers. And so the x-axis is actually just the real part of the complex number, and the y-axis is the imaginary part. So if I point to any arbitrary pixel, the real part is whatever matches up to this horizontal location, and the imaginary part is where it is on the vertical plane, right? So the Mandelbrot set is just a set of single-dimensional numbers, not two-dimension, just, should I say single? Yeah, single-dimensional numbers. They're not vectors, they're just single values, but they're imaginary numbers. So when you plot them, you can plot them on a 2D plot, and you're doing that just to show a set of imaginary numbers. Make sense? Okay, so the idea is that an arbitrary complex number, so if you give me any complex number C, I can tell you, well, I can't tell you, but I could have a computer tell you whether that number is in the Mandelbrot set or not. It makes sense? And then if you plot all of them, then you see the picture, right? So, yeah, I already said that. So the black pixels are in the set, the colored pixels are not. All right, so to generate the picture, or to tell if a number is in the set, it's based on this polynomial. It's p sub c of z equals z squared plus c. Now you might say, wait a second, what? I thought you said there's only one value that you're testing if it's in the set or not. Why is there two variables there? Why is there a c and why is there a z? Well, it's the c that actually matters. The c is the value you're testing. So if you come to me and say, I want you to tell me if value c is in the Mandelbrot set, then c is the value you're testing. Z is a variable that starts out as 0, and the way you use it is you evaluate the polynomial p sub c with z just being 0 initially, and then it comes back with an answer, right? And then you take that answer and you plug that back in as z, and you do it again. And you get the answer out again, and you plug that value back in as z. So as you're doing this, the value of c stays constant. That's just the value you're testing. The value of z starts at 0, and then every time you evaluate the polynomial, you update z with that value. So it's sort of recursive in that way, where you take z is 0, and so if z is 0, 0 squared is 0. So p sub c of 0 is just c, right? It just pops back c. So then I take c, which is again the point I'm testing, and I plug it back in as z. So the second time I evaluate this, z and c are equal, right? But then I'm going to end up with a third number, and I plug that back in and in again as z, right? And I keep doing this over and over again. So it looks like this. It's like p of c of 0, then I look at p of c of p of c of 0, then p of c of p of c of p of c of 0, and so on, right? If you were to write this out as a sequence, right? So you get a sequence of numbers, imaginary numbers, right? You guys with me?
When it says it does not diverge in infinity, that means it's going to have a limit.
Well, yeah, I'm getting to that. Okay, so if you have these sequence of numbers, it's going to behave in two possible ways. It will eventually diverge to infinity, right? It'll keep getting bigger and bigger and bigger forever, right? And it kind of makes sense. I mean, look at the polynomial, z squared plus c. You're taking a number and you're squaring it, squaring it, squaring it, squaring it, squaring it. Of course it's going to blow up to infinity, right? Has to. Well, no, because they're complex numbers. Remember, a complex number has an imaginary part that has an I, and if you square I, it's -1. So because of the imaginary part, just because if you have an imaginary number and you keep squaring it, it's not necessarily going to go to infinity, although it might, right? But because it's imaginary, it might just kind of hang around and don't explode, right? It makes sense, right? Because you got the I, the imaginary. If you square I, it's -1. That -1 might bring it back down. You know, it might kind of push it down towards 0 instead of making it explode, right? So you calculate this this sequence, and depending on what you started with, depending on what c was, the starting value, it may explode to infinity, or it may just not. Maybe it might just sort of not diverge. It may just kind of waffle around 0, right? So if it never diverges, it's part of the Mandelbrot set. But if it diverges, it's not part of the Mandelbrot set. But the pixels that are brightly colored, the brightly colored pixels represent values that start out staying, kind of hanging around, and then at some point after several iterations, then it explodes out to infinity, right? So the ones that sort of take a while before they blast off, those are the brightly colored ones, right? So basically you calculate the color according to how long you can generate that polynomial before it goes and diverges, before it lifts off and blasts away, right? Specifically, what you're looking for is that this Mandelbrot set, by the way, to give you an idea of the ranges here, this edge is -2 on x. The real part is -2. And over here, the real part is 1. So this is -2 over here, +1 over here. Vertically, this is -1, and the top is +1. So all the imaginary numbers, the range of imaginary components of all the black pixels are all between -1 and +1, right? And the real numbers are all between -2 and +1. So that's -2, +1 on the real side, -1 and +1 on the imaginary side, right? Which means that if you go to the origin is right about here, not quite in the middle, but it's in the middle vertically, but horizontally it's over to the right a little bit. That's the 0, 0, the origin. Actually, it's probably right about, I guess it's probably in the middle here of this bulb. I think that's 0, 0, right? So obviously 0, 0 is in the Mandelbrot set, which makes sense because z squared will always be 0. So if you take a circle, you put a circle around the origin that has a radius of 2. So you take the origin and you draw a circle with a radius 2. As long as the value of the Mandelbrot polynomial stays inside that circle, that means you're still inside the boundary, the area, right? The minute you go out of that circle is the point at which you consider it to have been diverged, right? So if you just count the number of times you can run the Mandelbrot without going outside the circle, that's your color. And you can generate the color however you want. In this case, they use like a yellow and red sort of color motif. You can, the greatest part about this lab is that every group likes to, or a lot of the groups like to come up with their own color function. So everyone, like a lot of the groups will get different colors here, so you get different pictures, which is kind of neat. Yes?
You said for the real part it's from -2 to 1.
Yes.
The real part,
Yes.
which is the x.
Yeah, the x is real, the y is imaginary.
You said it's from -2 to 1.
Yeah, -2 is the real negative. This is negative. It might be -2.5. I don't remember. I think this picture. I think this edge is -2, and this edge is +1. So the real part goes from -2 to 1. The imaginary part goes -1 to +1. One of the issues, by the way, here though, I'm going to point this out now, is that if this were a regular plot, then the bottom edge would be negative. Would be like the low side, right? And the top would be the high side, right? So, like if 0 was in the middle, this would be like -1 and the top would be +1, right? The problem is that that's not how the frame buffer works. If you're doing frame buffer stuff, 0 is at the top, the first row of pixels at the top. That's 0, row 0. And then when you go down, you increase the number, the vertical coordinate, right? The row number, right? So there is the way that you would plot this and the way that you enumerate the pixels vertically are flipped, right? So you have to account for that when you render it on the screen. But I'll get to that in a minute. Okay. Okay, so here's an example. Oh, well, first of all, let's quickly review. If you have a complex number, like say you have 3 plus 2i, 3 is the real part, 2 is the imaginary part. If you square it, you have to take the real part and square it. So the 3 gets squared, becomes 9. And then you take the imaginary part and you square it. So 2i squared is what? Is 4i squared, and I squared is -1. So 2i squared is -4, right? So if you take the 9 and you add that to the -4, then the result is 5. The real part of the product is 5, right? And then for the imaginary part, you got to cross multiply the imaginary part, which is 2i times 3 times 2. So the imaginary part would be 2 times 3 is 6 times 2 is 12, right? So 3 plus 2i squared would be 5 plus 12i. You guys remember that? Okay. So in general, if I were to call the real part x and the imaginary part y, and I'm doing that just because I want to be able to plot this thing on an xy plane, right? So if x is my, say x is my real component and y is my imaginary component, then if I have x plus yi squared, then that is going to be x squared minus y squared plus 2xy times I, right? So my real part is just to square the two. You just square the real and the imaginary parts and take the difference. That'll be the real part of the result. And the imaginary part's going to be 2 times the real part times the imaginary part. Okay? Okay, so here's a full example. So say I have a number like 0.5 is the real part, 0.75 is the imaginary part. Is it in the Mandelbrot set? Well, I'll start out the polynomial with a z value of 0. And so, as I mentioned before, if your z is 0, then the polynomial just spits back the c value at you. So the first evaluation is just going to be 5 plus 0.75i, right? But then I take that and I plug that back in as z. So now I have to square 0.5 plus 0.75i. I square that, and then I add the original c value to that sum, which gives me 0.1875 plus 1.5i. Okay? Now, at this point, I have to stop and say, has this diverged yet? And the answer is, well, I have to figure out if it's within a radius 2 circle. So you just use, to determine that, you would just take the real part, square it, take the imaginary part, square it, add them together, and take the square root of the result. That just uses Pythagorean's theorem, right? That will tell you the radius of, or it's a vector norm operation, basically. It'll tell you the distance from the origin of that vector, right? Obviously, it's going to be within 2 because neither one of those goes beyond 2. So far, so good. We're okay. So you take that result, you plug it back in as z once again, so you're squaring 0.1875 plus 1.5i. You square that, you add it to the original c value again, and now you get negative 1.7148 plus 1.3125i. Okay, turns out it doesn't look like it, but that value is actually outside of the radius 2 circle. That value right there disqualified this thing from being in the Mandelbrot set. And then if you keep going, then it just gets worse and worse. By the 4th iteration, it's negative 10, negative 12, right? Is with me? So the point of this is that you're calculating this polynomial over and over again, but the only reason you're doing it is to see when it diverges and if. But in the end, you throw away the value. Like all the values that you calculate, all the sequence of values, you don't end up doing anything with them. Unless you want to. Some people figured out that if you keep those numbers that you get, the sequence of numbers, if you hang on to them, if you keep them and you plot them, if you plot the sequence of values from keep doing that polynomial, you plot them, and then you plot the next one, and then you draw a line connecting the old value to the new value. And then you get the next one, and you draw a line to that value. It ends up drawing this weird shape like this, because it kind of goes, assuming, of course, you pick a number that is in the Mandelbrot set and doesn't diverge. It'll just keep drawing a line within this unit 2 circle. And somebody said that it looks like a picture of Buddha, believe it or not. And they called that the Mandelbrot set. I've never actually tried it, but it's a thing. But we're not doing that. We're just doing it just for the purpose of checking to see if the pixel eventually gets ejected out of the unit 2 circle. Okay. But in this case, this one is outside of the set, so it will not be a black pixel, but it will get a color corresponding to how many iterations it took before it left, and it would be 4, I think. 0, 1, 2, Actually, I don't know why I said 4. It should probably be 3. 2 or 3. Yeah, I need to fix that. It should be 3 iterations. So this will not be a brightly colored pixel, it will be a dim pixel. Here's another example, 0.25 plus 0.5, it just kind of you can see it just kind of waffles around. I calculated it all the way to 1,000 iterations, and it's still within the set. Okay, so so that's the deal. The problem, though, is that how does your program know if it will never diverge? As you keep running the polynomial. Like a set within the Mandelbrot set will allow you to keep applying that polynomial infinitely, right? Without the z value, without the return of the polynomial ever going outside the radius 2 circle, right? So how does your code know that we'll never exit the circle? Well, it doesn't. In fact, as far as I know, there's no way to know that for sure. But if you set an upper limit on the number of iterations, then you can be reasonably sure. So like, for example, if you were to set the iteration limit to 1,000, you can run the polynomial 1,000 times, right? And if it doesn't exit after 1,000 times, you can assume that it's in the Mandelbrot set. Does that make sense? Okay, so that's the idea. By the way, computationally, if you have to run it 1,000 times, it's going to take a long time to figure out that pixel, right? Whereas if you have another pixel that you're evaluating that's over here in this area here, it's going to go really fast because these pixels diverge really fast. So when you're plotting this thing, you'll find that your CPU gets real slow in the black area, and it gets much faster outside, right? So that's something you have to consider. It's not like the image transformation program that we're doing now that sort of runs at the same speed all the way through. Okay. Okay, so there's a few problems that need to be solved for this. How are you gonna discretize the complex numbers onto your pixel? So you've got 320 by 240 pixels, and you want to associate each one of those pixels with a unique value that's sort of spread across some range, right? So you have a range, you have a horizontal range and a vertical range, and then you're going to decompose that range into a grid of pixels. And each of the pixels is going to be a regularly spaced, you're going to have grid points that are regularly spaced in horizontal and vertically, right? Make sense? Okay, so that's what I mean by discretize. Also, how do you determine if a pixel's in the set, and how do you zoom? Oh, we also, by the way, want to zoom in. Sorry, I should have mentioned that earlier. So these fractals are only interesting if you pick a point somewhere in one of these sort of brightly colored regions and you zoom into it. Otherwise, they're kind of boring. Like if you zoom into a black area, it just quickly becomes a black screen. And if you zoom into like an area even right around here, the whole thing will just become pink, right? You want to zoom into an interesting spot, and if you do that, you get to see not only some crazy psychedelic shapes, but you also get to see how it's sort of these patterns repeat over and over again the more you zoom in, right? But there's a catch, and this is something I didn't realize until I actually wrote the code. When you're zooming in, this is not intuitive, but when you're zooming in, you can't zoom at a fixed rate. You can't just zoom at this. You can't just like, it can't be like you're just like getting closer and closer and closer to an area of the picture at a fixed, at a constant sort of fixed rate. The zoom has to be exponential. You have to zoom in exponentially. You have to zoom in faster and faster and faster as you go. right? That's the way it works. That's when you see the repeating shapes. Okay? So, so that's the idea. We want to pick a point and zoom in, and you get to see the effects of that. And then, of course, we want to. The reason I chose this application is it's simple and it's graphical and its performance. You know, it's computationally expensive. So by doing stuff to speed it up, you get to see it actually speed up. It gets the performance translates into FPS, frames per second. But the other reason is because it's embarrassingly parallel. Probably a lot of graphics applications are embarrassingly parallel. Embarrassingly parallel means that there is really there's very little synchronization that has to be done, and there's no dependencies between the pixels. So you can calculate all of the pixels at the same time, right? You just have to synchronize after the frame is done, like as we do with the barrier, right? So in other words, there's a lot of exploitable parallelism here that we could take advantage if we have a whole bunch of CPUs or a whole bunch of functional units or a whole bunch of whatever that you want to throw at this, right? That's how GPUs work, by the way. GPUs have a big collection of very simple cores because that sort of architecture matches graphics really well because basically they're designed to calculate every pixel in parallel, right? So you can throw as much hardware as you want, and you'll get a very good return back from that until you have more processors than pixels. At which point, probably have a harder time getting performance. Okay, so how do we plot the space out? Let's start with that. I came up with what I think is a really easy way to do this. You keep track of your minimum and maximum x and y. So like the picture I showed you before, I said that the minimum x is -2, right? And this is 1, right? -2 to 1. Say that right? Yeah, -2 to 1. And the y is -1 to +1. So your range in this direction is 3, and your range in the vertical direction is 2. So all you have to do is divide up that range by the number of pixels you have in that dimension. So if my max minus my min is 3, and I know I have 320 columns in the frame buffer, I just have to divide that range of 3 by the number of pixels, which is 320. And that gives me the total spacing in between the pixels in the horizontal direction, right? Likewise, the vertical direction, if I take my max, which is 1, and I subtract my min, which is -1, I get 2, and I have 240 pixels vertically. So I just take 2 and I divide it by 240, and that's the spacing between the pixels. And then all I have to do is add the minimum, which is -1, right? So if I want the row number, I say -1 plus the spacing of the pixels times the row. And that gives me what that pixel maps to. Okay? Makes sense? So I'll go into a little bit more detail of that in a second. So I keep track of the minimum x, the minimum y, the maximum x, and the maximum y. So you just keep track of that for every frame. And so the x, so this is what I was describing. So the x is let's start with this. You take the maximum x minus the minimum x. That's your range, right? Your horizontal range. And you multiply that by the column that I'm on, divided by 320, because this number is the ratio. This is how far across the horizontal span of the picture I've gotten, right? Column, so like if I get to column 160, I'm halfway through. So that ratio is 1/2, right? If I'm at 0 is 0, and I'm at 319, that means I'm almost at 1, right? because 319 divided by 320. So I take the range, I multiply it by how much of that range I've covered with a given column number, and then I add the minimum x, it's offset, right? So what this line of pseudocode does is it takes a column and it spits back a number of where I am in the plot, right? But it depends on the x, the minimum and the maximum x and y, which define what part of the space I want to plot on my screen, right? Now, as you might imagine, as we zoom in, that minimum and maximum x are going to close on top. They're going to get closer and closer, right? Like when I zoom in, the way I zoom in is I just take the minimum and max and just push them closer and closer together, which will appear as I plot them as if I'm looking closer and closer at the plot, right? Make sense? Likewise, so y is a little bit more complicated because of what I mentioned earlier. With the y, with the vertical, I have to flip it upside down. So it turns out it's easy to do that. You just take the row, and you take 239, which is the maximum row, and I subtract it from the row, and that becomes my, the new row as it's seen by this calculation. So in other words, what this means is that if my row is 0, what does that mean? It means I'm at the top of the frame buffer. I'm at the top of my monitor. Row 0 is the top row. So what I really want that to be, in terms of the mathematical value, should be 239. In other words, I don't want it to be my smallest row. I want it to be my highest row. It's the smallest row in terms of my frame buffer, but it's the largest one in terms of a Cartesian plot, where going higher is adding to your vertical value, right? You guys with me? So easy fix. You just say 239 minus row, and then everything else is like above. Make sense? Okay, so then you might say, well, how do I figure out max x and min x and max y and min y? That is going to be calculated in terms of your target. So you're going to have a target point. So you're going to pick a point to zoom in. So basically, you render the whole frame. You render a frame. You just render this, actually, this frame. You use the values from here. -2, +1, -1, +1, right? Plot this. Then your software is going to decide where it wants to look, where on this plot it wants to go farther in, it wants to zoom into, right? And you can decide that however you want. Obviously, you want to zoom in on one of these brightly colored regions. So you want to pick a pixel that has a high iteration count before it diverged. So some groups will do they'll find just whichever pixel had the highest, right? Find the highest. Other ones will say, well, let's find the first one that was 90% of the maximum. So if your maximum iteration count is 500, before you give up and just say, oh, that's got to be in the Mandelbrot set, then 90% of that is going to be 450. So the first pixel that hits 450 iterations will be our target point, right? Some groups do it that way. It's up to you. I'll leave that part to you. But find an interesting spot and then set that as your target, right? And so once you've got the target, then your minimum and your maximum x and y are just around that target, right? You just take the target and you put it in the middle, so you subtract something from the target and make that your minimum, and you add something to the target and you make that the maximum, right? So that way, you're zooming in to the target, and your minimum and maximum x and y are just closing in around that target. Make sense? Okay. Yeah. Okay. So here's some pseudocode for the whole. Oh, sorry. Actually, this is not the whole thing. This is just the iteration loop. So the way this works is you have an x and minimum and maximum x and y that you've preset. So those are set up, and then you go through every row and every column of your frame buffer. So you just have the same loop you guys have now. For I equals 0 to 239. For j is from 0 to 319, right? So I is the row, j is the column. Actually, I call them just row and column here. Sorry, row and column. So row and column is your I and j. So this code is inside of your double nested loop for your, for every row, for every column, right? So the first thing you want to do is take that and transform it into a C value, which I call x0, y0, where x0 is the real part and y0 is the imaginary part. The way you transform it according to these two calculations, these guys right here. Okay. Now you might say, why y0? What's the 0? Why do you call them y0, x0? Because that's like the initial x and y, right? And so it's C. The C value is x0, y0. So then you go into this while loop, and every iteration of this while loop, your goal is to calculate a z value, right? So you initialize iteration to 0, and then you say while, you also initialize x and y to 0. So this part's a little confusing because z is x and y. That's the value that keeps changing as you go through this, right? That's your sequence of numbers. C is x0, y0. So you set x0, y0, and then you go into this while loop, and then you're going to keep changing x and y. But you're going to start them off at 0. So you set x and y to 0, and then you say while x squared plus y squared is less than 2 squared, which is 4. As long as that's true, then I'm going to calculate a new z, and you just do it with these 3 lines of code, actually. So you calculate x temp, which is the real component, which is, remember from, when you square a complex number, the real component is going to be x squared plus x squared minus y squared. And then you have to add x0, because remember, you have to add c, right? And then we assign that to x temp. Why? Because we have to calculate the imaginary part first before we commit that to x. So you calculate y as the imaginary part's 2 times x times y plus y0. And then you take x temp and you put that into x. And then you increment the iteration, right? So essentially all this is you're squaring z and adding the c. Yes?
Is x temp the real part?
X temp is the real part, which will become the real part, but you can't put it in the real part right away because it'll screw up the imaginary part calculation, right? So that's why you have to have that in a temp value. I've never found a way around that, by the way. You have to keep that temporary until you calculate y. Then you can commit x temp to be x, right? It's because of a data dependency. You can't update x until you're done with the old x, right? But yes, x is the real part. Oh, because y was the imaginary part. So like if the imaginary part was 2, it was 2i. So you have to square the 2 and you square the i. When you square the I, you get a -1, right? So it's subtract. That subtract is resulting from squaring I, right? The imaginary part. Okay, so that's the while loop. And once you get through that while loop, I'm sorry, you have to also check to see if the iteration, you don't want to keep going through the while loop infinitely, right? You have to stop, you have to give up at some point. So that's why it says and iteration less than 500, right? If you get through the while loop, if you break out of the while loop because the iteration count hit 500, at that point you assume that the pixel must be in the Mandelbrot set, so you'll color it black and print it to the screen. If that's not the case, if iteration isn't 500, it means that we broke outside of the while loop because the z value, the norm of the z value exceeded 2, right? It went outside the unit 2 circle. So at that point, the color needs to be determined as a function of the iteration. The higher the iteration, the more brightly colored it is. But see, here's the problem though. The color, as you guys know, the color is a vector, the red, green, and blue value, right? So the problem is you need to convert a iteration value to a 3-dimensional color value, right? And this is where the uniqueness part comes in, because depending on what you need to basically come up with a color map, like a color spectrum, right? So one way to do that is to take the iteration and use it to calculate red, green, and blue, but do it differently for red, green, and blue. So if you take the iteration and you multiply it by 8 and you make that the red, you multiply it by 4 and make that the green, and multiply it by 2 and make that the blue, this will give you a red, orange dominated palette, right? But if you prefer something cooler, you can make the blue the value that has the most weight, right? Multiply that one by 8, multiply red by 2, right? But the important thing to keep in mind is that the maximum value for red, green, or blue is 255. So when you're multiplying the iteration, you don't want that to exceed 255 or you'll bleed one color into the other, right? So you need to clamp these values to 255. So once you multiply by iteration, if that number is greater than 255, you have to make it 255, right? It's called clamping. Or sometimes people call that saturating arithmetic, right? The other problem is, you might be thinking, wait a second, the iteration goes to 500. So if a pixel is really close to being in the Mandelbrot set and diverges at like 400, then that's just going to blow the color out to white. Guaranteed. You'll just get a white pixel, right? You don't want that. You want there to be more subtlety, right? So how do you deal with that? This is my own solution. You might come out with something different. My sort of simplistic solution to that problem is if you dampen those colors by the zoom factor. So what happens is, as you zoom in, the more you zoom in, the higher the average iteration is going to be for the pixels, because you're zooming in on a very small area, and the number of iterations is going to generally be higher in general as you zoom in, right? So if you attenuate the color by the zoom level, by dividing each of those by whatever zoom you're at, that will make the pixels darker and darker as you zoom farther and farther in, which is what you want, because otherwise, as you zoom in, it's just going to get blown out to white really fast. You know what I mean? It's going to be like flying into the sun, right? But if you divide by the zoom, it'll sort of even things out as you get closer. And I get pretty good results, at least in my opinion. There's other ways to do that. If you search online, you'll find there's tons of stuff on the internet about this, by the way. In fact, there's really cool YouTube videos too where people went a little crazy with this, and they used a really large-scale supercomputer to calculate really insane zooms on this thing. But I'll leave that part up to you. Just make sure that you don't bleed, because if you bleed it, it'll turn into a rainbow and look really bad. Okay. One of the other things you'll notice, depending on how performant your software is, if you zoom in, as you zoom in, what's going to happen? The spacing between the pixels gets increasingly smaller, right? Eventually, you run out of precision, right? You'll like we're going to use floats initially. Floating point, single precision floating point. Or you can use double precision, but then it'll be way too slow because we don't have hardware support for that. But if you use, I did this little plot where as you increase the zoom level, and you increase the zoom level exponentially, you essentially lose a bit. I mean, what you're basically doing is that it's costing you a bit of precision every time you zoom in. So eventually you run out of bits, you run out of precision, and the picture will start to block up. You'll start to lose the ability to distinguish between one pixel and the next one, right? So when does that happen? Well, with double precision, it would take about 80 iterations before the whole screen becomes one pixel. Okay. So, but that won't be an issue. This will be a little too slow, I think, unless you guys are able to tune this code really well. Okay, so one last thing is, let's talk about the zooming. I think this is the last topic. So the zooming is based on an exponential tightening of the minimum and the maximum x and y around the target point. Specifically, one way to do that is to say min x is the target x minus 1 divided by 1.5 raised to the zoom power. The problem is you don't want to use an exponentiation in this because that's going to slow things down. You know what? Actually, come to think of it, it probably doesn't matter that much because you only have to do this once per frame. So it's not a big deal. Actually, the way that a lot of students do this though is instead of running the power function, I think it's a little bit easier, or probably maybe even a little bit more readable. If you have a variable called radius that gets initialized to 1, and then every time you get done with a frame, you multiply radius times 1 over 1.5. Right? And so that way it'll just, it'll keep that progression. It'll act like an accumulator. And then the radius is what you'll subtract from the target and add to the target to define the minimum and maximum values. Make sense? Okay. So that's all you got to do to zoom. Okay. So as far as the lab goes,
We actually go over the lab sheet.
yes, lab sheet. So the lab sheet says so I got this due on 4/15. Initially display the fractal from negative 2.5 Yeah, sorry. The real part is the x. So negative 2.5 to 1, x, y, negative 1 to positive 1, right? Hopefully I didn't screw that up earlier. Yeah, negative 2.5 to positive 1 for the x. That's the horizontal. The vertical is negative 1 to positive 1. The problem with that, by the way, is that ratio, that aspect ratio, is not the aspect ratio of your monitor. These monitors are 4:3 aspect ratio. And so this aspect ratio would be 3.5 divided by 2. Right? Not the same. So when you plot this, it's going to be squished a little bit. But as you zoom in, after the first zoom, you can adjust it and use the right 4:3 aspect ratio. By the way, how do you do that? It's easy. Remember that radius thing I was just talking about? All you have to do is initialize. You multiply that. I have it here somewhere. Yeah. So instead of like 1 over 1.5 raised to the zoom, you do that for the x, and the y is 0.75. That'll ensure that you keep the right aspect ratio. And then if you do it this way, you just initialize radius to be, 1 for the horizontal and 0.75 for the vertical. Right? So it's not too hard to do that. But otherwise, you don't want your view to be squished.
Should there be an I near that negative 1? It's going to be the x. The I is only referred to the there.
I'm sorry?
Should there be an I right there, or should it not be? For the negative
No, the x is the real,
Just the real part.
right,
Okay.
and the y is the imaginary. Okay, so to identify the zoom point, use the pixel value that diverged after at least 50% of your iteration limit, but you have flexibility here. You can define this however you want. Like I said, you're looking for a pixel that's bright colored, right? So you don't want something that hit the iteration limit, and you don't want something that has a low iteration count. So find something that's high. I usually use 0.9, right? 90%. That's what I always did. Use an exponential zoom rate. At each zoom level, re-render the frame. Use floating point values for generating the fractal. Begin with 1 processor and then scale up to 4 processors. So we want to add 2 more processors. Hopefully by now you guys should be pretty comfortable with that. Obviously adding 2 more is going to add a lot of wires. Yes?
Do we have to add another on-chip memory?
The barrier will work with just the one on-chip memory.
But you're saying we're adding 4.
Mm-hmm.
So you would still just keep.
Yeah, just to give you a little bit more detail on that, the on-chip memory that you added had a capacity of, I think it was like 1 kilobyte or 4 kilobytes. So it holds something like 1,000. It has enough room for 1,000 CPUs for the counters, because you only need the way the barrier works is you have to associate 1 counter per CPU. So you have plenty of room in there for counters. Although one of the problems you have to solve with this is the minimum and maximum X and Y have to be the same on all the processors, right? So that means that your target X and target Y have to be the same on all processors, which means that you're going to have to have one processor decide where you're going to zoom, and they all have to agree on that. So you're probably going to want to use the on-chip memory to store that as well. But that's just another two words. Yes.
We had like another processor. We also have to add another floating point unit.
Yes, you do. Yes, yes. Thank you. Yes, you do have to add 1 floating point unit for every processor. Yes.
And then how do we offset the address for the other processors?
Oh, yeah. Just add 8. That's also a good question. Yes.
From 8 to 16.
Right.
Okay.
Yep. 16. But remember, you're in hex, so 16 is actually 10,
Okay.
and then the next one will be at 18 in hex. Yep. Yeah. Good question. Okay, so the performance measurement for this is a little bit more involved because there's a couple of things you have to consider. One is that depending on what pixels you process, depending on how many black pixels there are in a frame, the slower the frame will be. So if you're measuring the time per frame, you're going to want to do an average over like 4 or so frames, right? So that's one thing. But the other thing too is when it comes to optimizing it, what you care about here is the innermost loop, right? What's the innermost loop? It's the while loop. It's the loop that calculates it's the loop that calculates the polynomial. That's the innermost loop. That was the loop I gave you the pseudocode for. So because almost the whole time of your program is going to be spent in that little while loop, that's what you want to focus all of your analysis and tuning on, is that little loop. So we want to figure out how many cycles and how many instructions are in that little loop, right? So we're focusing on that. And actually, in this case, I don't tell you to do the number of instructions. In this case, we only care about number of cycles. But I do ask that. So in other words, what I'm saying is you don't have to use GDB to count the number of instructions, but I do want you to calculate the number of cycles it takes per floating point operation. And you might say, well, how do we know how many floating point operations there are? You just count them, right? You just go to the code and count, literally just count the number of operations in there, right? The number of multiplies and adds and subtracts, right? Make sense? So what are we hoping here? Well, again, like 1 instruction per float would be ideal, but you guys know by now that that's not realistic. even if you had nothing but the floating point instructions, those things take like 4 cycles or 5 cycles each, right? But we want it to be as low as possible, right? We hopefully it's not 10,000 cycles per floating point operation. So we want to figure out where we are there to get an idea of what sort of overhead we have just to get the floating point operations through, right? Okay, so 1 is average time to generate each frame for at least 4 frames. Average number of clock cycles to compute and paint each pixel over at least 1 frame. Obviously, once you have 1, you can get 2 just by dividing by the number of pixels. 3 is number of cycles to compute 1 iteration of the polynomial evaluation loop, which is the innermost loop. And number 4 is number of cycles per floating point op. And we want to do that. Your report needs to contain all of the things that you decided on, like iteration count and method for finding the zoom point and the color calculation. Why is this important? Because your performance numbers are going to depend on how many iterations you go through. So a lot of you guys are going to probably decide at some point while you're debugging it that you're going to crank your iterations down to like some really low number, like 50 or 100 to speed things up. But you'll notice that when you do that, you're going to see false positives on your screen. You're going to have pixels, you're going to have black pixels interspersed like little Swiss cheese holes because your iteration count, that'll happen when your iteration count is too low and your program falsely decides that certain pixels are in the Mandelbrot set that aren't because it gave up too early, right? So, but that's fine. That's still a valid way to debug. But just make sure that in your report you tell me what your iteration count is, because that gives me an idea of what sort of workload the CPU has. Make sense? Okay, and that's it. Any questions? Yes?
So like that 1 through 4 thing that we have defined, that's for like each processor though, like it's like 1 processor, 2 processors?
Yes. Yeah, you want to see how those numbers, thank you. Yeah, how those numbers change over as you scale up.
Okay.
Yeah. We hope that the number of cycles to do a frame should be, should have and then third and then fourth or so, right? Ideally, as we scale up. The number of cycles per floating, or the number of cycles for the innermost loop will probably not change too much at all as you scale up the number of processors, but it will increase if we run into contention, right? If the processors have to fight for on-chip resources, then you'll see the number of cycles in the innermost loop will actually increase as you scale up the number of processors, right? So you'll see the total cycles will go down, but the innermost loop cycles will go up, possibly, right? Okay, thank you.